Hey everybody, welcome to class. We'll get started in a minute here. Here's the usual attendance form. Please go do the thing. We'll start in a minute. I want to end that video. I'm something creative to do. Okay, cool. I should erase this stuff. Okay. I know I didn't watch Rodriguez's class today, so I don't know what he covered. My plan for today was to mostly talk about problems that were similar to the exam that you guys have in Rademacher's class. I can also do some stuff similar to the practice test that Carlson posted for you guys, which looks...
James, for Rodriguez today, we just went over, I think, its applications of multivariable derivatives.
Okay.
So finding the optimization, but with multivariables, basically.
Oh, okay, sure.
So I think starting next week, we're probably going to start doing double integrals. I did talk to him. He mentioned that we're going to cover double integrals with rectangles. And I think for situations where we have to take a double integral of where the base is like a weird shape or maybe a function like a triangle or something. He did mention we're going to do one more optimization problem, such as I think a cube inscribed of a sphere, but that's what I asked him about during his office hours today.
Okay. All right. We can definitely address some of that. So let me just ask you, for the optimization, were you guys using Lagrange multipliers?
Using what again? Can you repeat that?
They're called Lagrange multipliers.
I've never heard of that term.
That's fine. Sometimes it's something people do, if not.
I think there's some problems in the textbook for chapter 9, section 6, where it does have some optimization problems towards around number 20s to like 30, I believe. It ranges from you have a volume of this number, try to find the maximum or minimum amount of cardboard to use, to something like what is the shortest distance between this plane and point, all the way down to you have a sphere and a cube. Yeah.
So maybe we'll look at that today, but I think for the people in Rademacher's class, we should kind of go over, I came up with some problems similar but not the same to his exam questions, just to kind of help you guys remember what exactly, whoops, sorry about that. Remember what we're supposed to be doing. So let's do a few problems. So it'll be a good review for everybody in general as well. And then if we've got time, we will do some other stuff. So, let me pull this up here. So consider the function f of xy equal to the natural log of, what do I got here? X squared minus y squared. I want to find the domain. And I want to find the, what do I got here? The level curves at z equal to 0 and z equal to 2. Okay, so domain for this kind of thing is pretty straightforward. For a logarithmic function, the insides have to be positive. For a square root, the insides have to be non-negative, right? So here I'm going to say x squared minus y squared is greater than 0. If it was a square root, I would say x squared minus y squared is greater than or equal to 0. there's a couple ways you can solve this. One way would be to say x squared is greater than y squared. So that's going to mean that the absolute value of x has to be bigger than the absolute value of y. Right? X has to be further away from 0 than y is. So x could be -5 and y could be 3. That'd be fine. X could be -2 and y could be -1. That would also be fine. Another way you could solve this would be saying by factoring x minus y times x plus y has to be greater than 0. So then these both have to be positive or both have to be negative. So this seems harder. I don't like this already. So I would just do it this way, and then I would say something like, oh, okay, well, so I'm going to look at the line x equal to y. I don't want that line. I'm going to draw a dash. If I did want to include that line, I would draw it not dashed. I'm also going to get the line x negative x equal to y. So these two lines are kind of where I'm having things change. And I'm going to test some points. So I test the point 1, 0. Is 1, 0 in my domain? If I plug in 1 for x and 0 for y, is this inequality satisfied? So if I plug in 1 for x and 0 for y, 1 squared is greater than 0 squared. So this is in there. So this would be in my domain. What about down here, or up here, if I plug in 0 for x and 1 for y? Well, that's not going to be in my domain because if I plug in 0 for x and 1 for y, I don't satisfy the inequality. Similarly, over here, if I plug in -1 for x and 0 for y, I am satisfying the inequality. Right? -1 squared is greater than 0 squared. So I want all this. And then if I plug in 0 for x and -1 for y, it doesn't work. 0 squared isn't bigger than -1 squared. So there's my domain. It's kind of crazy looking. I don't think he asks you to graph the domain in the test, but so if I was going to state my domain, I would probably want to write it as the set of all x comma y such that x squared minus y squared is greater than 0. Another way you could state this, we can basically see that x has to be bigger than y, or x has to be, no, that's not right there, is it? Yeah. You could say this as x is bigger than y if they're both positive, or x has to be more negative than y if they're both negative. That's another way you could say this. Again, I wouldn't set this too much because your problem is not like this exactly, but yeah. As far as the level curves, so if I'm the level curves of this, you're just going to set your function, your z, equal to these values. So z equals 0. And then getting, let's see, 0 equal to the net. I should do this on the other side. Sorry. So I've got z equal to 0. I've got 0 equal to the natural log of x squared minus y squared. And then I'm going to try and rewrite this as an equation that at least makes some sense to me. So I'm going to do e to the 0 on both sides. Or if I had like 0 equal to the square root of x plus y, I would square both sides. And then e to the 0 is 1 equals x squared minus y squared. So this is an equation you might be familiar with. When you have x squared minus y squared equal to a number, or y squared minus x squared equal to a number, it's a hyperbola. And if x is 1, y is 0, I get the point 1, 0, and -1, 0. And it looks like this. And it's supposed to be symmetric. Mine is only super symmetric. Again, Right? You're just trying to see what the graph looks like when you set z equals to a certain value. And then for z equal to, I think, 2 was another value. Yeah, for z equal to 2, I'm going to get 2 equal to the natural log of x squared minus y squared. So e to the second equals x squared minus y squared. So x squared minus y squared equals e squared. That's just a number. It's still going to be a hyperbola. It's the same sort of equation. But now instead of x being 1 and y being 0, when y is 0, x gets to be e. So I'm over here at e, comma 0. And I'm over here at negative e, comma 0. And it looks similar. It's still a hyperbola. It's just further out. And so when you're graphing these level curves, you probably are supposed to graph them both on the same xy coordinate system. And you should label them, right? This one is the one z equal to 2. And this one is the one z equal to 0. Do make sure you label your level curves. Okay. So I'm just going along doing problems similar to these. The second one isn't so bad, but I remember a few of you asking me before kind of what that meant. So actually, let me write a similar question that I have. Also, please feel free to stop me along the way. Just speak up or type something in the chat, although I don't always see you type in the chat until later. And here's the attendance. Come on. Here's the attendance one more time. I think you guys have been perfectly great about everybody doing it. So let's say I had this limit. The limit is x, y goes to 0, 0 of the function x cubed plus 4y cubed over 3x cubed minus 2y cubed, the second power. And I'm even going to tell you, show that this limit does not exist by computing the limit along the positive x-axis and along the positive y-axis. Okay, so when people say this, what they mean here is y equals 0. Right? If I'm on the positive x-axis, it means y is 0. It also means, I guess, that x is greater than 0, right? If you're on the positive x-axis, x is supposed to be positive. Similarly, along the positive y-axis, x is 0 and y is greater than 0. So when someone says this, all they really mean is you're supposed to plug in y equal to 0. So to do this part, I'm going to do the limit as x, y goes to 0, 0. Sorry, I'm plugging in y equal to 0. As x goes to 0, I'm going to just, well, we'll see in a minute here, of x cubed plus 0 over 3x cubed minus 0 squared. Now, since it does say along the positive x-axis, you probably should actually write it as the limit as x approaches 0 from the right, since you are on the positive x-axis. And then we can simplify this. So the limit as x goes to 0 from the right, x cubed divided by 3x cubed, the x cubed cancel, and you just get 1/3 squared, the limit of a constant, just the constant, which is 1/3 squared, which is 1/9. In a similar way, to do the along the positive y-axis, we do the limit as y approaches 0 from the right, and now we're plugging in 0 to the x's. So 0 plus 4y cubed over 0 minus 2y cubed to the second power. The y cubes cancel. 4 divided by negative 2 is, well, negative 2 squared, and the limit of a constant is just a constant. And then since these two limits on different paths don't have the same value, these are not the same, So then we can say this limit does not exist. So that's how we do a problem like that. Okay, let's look at a linearization of a vector value function. It's always challenging. So here's a vector value function. It's, sorry, what did I write down here? Where'd you go? Great example that I had. Yeah, so here's my vector value function. So it's equal to e to the x squared y, the first component, and sine of pi x plus y, the second component. And we want to find the linearization of this vector value function. So find the linearization of this function at the point, what did I pick here? 2, 0. All right, so as you have to remember, this is going to be, so the linearization is also a vector value function. And it's going to equal the original function evaluated at the point of linearization plus we're going to have this I should probably write this, sorry. I always feel so it's the part, it's so this row is the partials of this. So like if I call this G and I call this H, then this 2 by 2 matrix has the partials of G in the first row. So Gx, Gy, and the partials of H in the second row, times x minus 2, y minus 0. Right? Usually if it was just one function, right, if our function wasn't vector value, right, if it was just a regular function, it would just be the gradient of that function dotted with the x minus x naught, y minus y naught. But since we have, ooh, my lights just flashed for a second. That was weird. Since we have two different functions making up the vector value function, each of the functions' gradients have to get dotted with this. So right, here's the gradient of this one, and you're getting it gx times x minus 2 plus gy times y minus 0, which is exactly the dot product of this gradient with this vector. Similarly, you're going to get the gradient, right? If you add these together, that's the gradient. Well, no, yeah, no, sorry, that's like the gradient of G, the gradient of H, and you're going to get this dot with that. Okay, so then we just write things out. So this function evaluated at 2, 0 is going to be e to the 2 squared times 0, which is just going to be 1. And then the second component is going to be sine of, you know what I haven't done yet? I haven't found the partials. Maybe I should back up for a second. Let's find the partials before I get too carried away here. So gx, the partial of this function with respect to x, is e to the x squared y times the derivative of x squared y, which is just 2xy. Gy is going to be e to the x squared y times the derivative of x squared y with respect to y is just going to be x squared. That's kind of in the way here. Apologies. What else? Hx is going to be the derivative sine of this stuff, is the cosine of that stuff. Times the derivative of that stuff, the derivative of pi x plus y is just pi plus 0. And finally, hy is, again, the derivative is with respect to y, so it's going to be sine of my, sorry, cosine of my stuff times the derivative of that stuff, which is just 1. And then you're going to plug in 2 and 0 for each of the things. So I'm going to start writing this matrix out. We're going to start writing the whole thing out. Here's what I get. F of 2, 0, which I said before was e to the 2 squared times 0. And then the bottom's going to be sine of 2 pi plus 0. Plus all of these things evaluated at 2, 0. So let's see, gx evaluated at 2, 0, you're going to get e to the 4 times 0, which is just 1, times 2 times 2 times 0. So you're going to get the 0 there. If you plug in 2, 0 here, you're going to get e to the 4 times 0, which is just e to the 0, which is 1, times 4. And you, now for the partial with respect to h, plug in 2, 0, you get cosine of 2 pi plus 0. Cosine of 2 pi is 1 times pi. And similarly here, cosine of 2 pi plus 0 is cosine of 2 pi, which is 1, times x minus 2 times y. And so if I was writing my final answer, I don't have room for anymore, I'm just write it right here.
James?
Oh, yeah?
Tell me, so at the last line of the first matrix, first matrix, it says e to the what?
Sorry, that's e to the x squared times y.
E to the x squared times y. Thank you.
And so that's why our partials are these and these. So my final answer is going to be this vector, or this 2 by 1 matrix, which is e to the 0, which is just 1. And this entry is sine of 2 pi, which is 0, plus this times this. Which I imagine you could probably leave like that, but you might want to multiply this out and say, I've got 1, 0 plus, when you multiply this matrix times this, you get 0 times x minus 2 plus 4 times y. When you do this row with that column, you get pi times x minus 2 plus y. So I suppose your final answer could be 1 plus 4y and 0 plus pi times x minus 2 plus y for this particular question. I don't really know how you're supposed to write your answer exactly, but one of these things should be fine. God, spraying water everywhere. Sorry. I'll you guys mind. All right, a couple more of these and then we'll do some other stuff. So I had a good example here. Where'd you go? Okay, yeah. So let's find the maxes and mins and saddles, right? I should really say find and classify all extrema for the function f of xy equals 9y minus 9x squared minus x squared y. Okay, so to do a problem like this, I feel like the light here is really terrible at the moment. Maybe my light off. Maybe I just have my brightness on my screen turned up. That's it. I just can't see on my computer because my brightness is turned down. Okay, so to find the maximums and saddles, we start finding the critical points. We set the gradients equal to 0. Really, you're just setting the partials equal to 0. Right, so we're setting fx and fy equal to 0. fx is going to be negative 18x minus 2xy, so that equals 0. Fy is going to be 9 minus x squared equals 0. So when I look at these, I usually try and look at the easier one first. Just one sec, apologies. Do that. So I try and look at the equation that's easier to solve. And to me, this one looks super easy, right? I can totally see that x is plus or minus 3. So here I'm getting x equal to plus or minus 3. Okay. Here I have to do some factors. I can factor in a negative 2x. I'm left with a positive 9 minus a y equal to 0. So here I'm either getting x equal to 0 or y equal to 9. Okay, so here's the thing. Both of these equations have to equal 0 at the same time. So even though x equals 0 solves this one, x equals 0 doesn't solve this one. So x equals 0 isn't going to be part of any critical point. On the other hand, y equals 9 is 5 here, and y can be 9 and x can be 3, and you'll get 0 here and 0 here, or y can be 9 and x can be negative 3. So our critical points are x equals 3 and y equals 9, or x equals negative 3 and y equals 9. So we've got 2 critical points, and now we need to classify them. All right, so let me go to the other side of the board. By the way, if you have, let me just look at one thing real quick here. So I see that a few of you aren't here, which is fine. So if you know people in Rademacher's class who aren't here, and I can think of one person specifically, let them know, and I'll probably send an email too, but let them know that we covered examples similar to the midterm, because I feel like this might help them do their midterm. So let's finish this problem. Right, I'll send an email, but you guys might know each other and be able to like send a text message or something to each other. So sorry, my critical points are 3, 9, and negative 3, 9. And my partials were, let's see, fx was negative 2x times 9 minus y. Let's do it now. You don't want the factor form if you're finding seconds. I was gonna write this, but I really want this. Negative 2x minus 2xy. And fy was 9 minus x squared. Okay. So then fxx is going to be negative 18 minus 2y. Fyy is going to be 0. And fxy is going to be negative 2x. So then capital D is going to be, let's see, this times this. So capital D is going to be this times this, which is 0 minus this squared. Now, here's what you should see right away if your D is equal to this. My D is always going to be negative or 0, right? There is no way this can be positive. I've got, right, this is equal to negative 4x squared. But whatever x is, unless it's 0, this is going to be negative. So I can see that when I plug in, right, d of 3 comma 9, I'm going to get negative 4 times 3 squared, which is going to be negative something. I don't even care what it is, negative 3 times. That means I have a saddle there. Similarly, if I plug in negative 3, 9, you're still going to get it being negative. So I still get a saddle. So both 3, 9 and negative 3, 9 are saddles. Yeah, it's a pretty good problem. Do be careful. It's easy to get confused with the critical points, right? If you get x equal to 0 and x equal to like other things, if you see that x equals 0 works here but doesn't work here, that means it can't be a critical point. So be aware of that. All right, I think I've got one more example I have for the Rademacher test people, and then we will move on to other things. So the next question is similar but different. And I'm going to go over what I actually designed here. Let's see, what did I come up with? I got you. Oh, let me see. I wrote a bunch of different problems because I was trying to make one that was good. Okay, yeah, sure. Let's say we have this function. F of x, y equal to 2 plus 2x minus 2y minus x squared minus x squared minus x squared minus y squared minus xy. And I want to find the global maxima and minimum on, sorry, let me see how to phrase this here. On the set, what have I got here? Let's say I did set of points x comma y where, yeah, x is between 0 and 3 and y is between -3 and 0. So a square, specifically the square in the fourth quadrant, right, the square here. That's the point 3, 0, that's the point 0, 0, there's the point 0, -3, here's the point 3, -3. So here's what we have to do.
James, can you
Yes.
start again for the part where it says global max / min on the set? What does the bottom say? -3 is less than or equal to?
Y is less than or equal to 0.
Okay.
So
Thank
so y is between 0 and -3, and x is between 0 and +3.
Thank you.
And so whenever you're describing a set where it's just x and y between constants, you're always going to get some sort of rectangle, which are the things with when you guys start doing double integrals. If you're doing double integrals, these are definitely the regions that we like integrating over the most because they are super duper easy. For this sort of problem, it's exactly like back in 17, right? We talked about this last class, right? We have to test all the endpoints, or I should say all the quarters, and then we have to find any critical points in the region and any critical points on the edges. So first, just regular critical points. So I'm going to find my partials. Fx is 2 minus 2x minus y. Set that equal to 0. And since I can't really like solve for anything by itself, I'm just going to isolate one variable. I'm going to rewrite this as 2 minus 2x equals y, or y equals 2 minus 2x. Similarly, fy is going to be, let's see, -2 minus 2y minus x equals 0. And here I would solve for x. And I would say x equals -2 minus 2y. And then I can use those two equations in conjunction with each other to find the critical point, or points. So I'm going to plug in x equal to this here and get, let's see, y equal to 2 minus 2 times -2 minus 2y. So y equals 2, -2 to -2 is +4, -2 to -2y is +4y. Subtract 4y, I get -3y equal to 2 plus 4 is 6. So I get y equal to -2. And then plugging that back in here, I'll get x equal to -2 minus 2 times -2, which is -2 plus 4, which is 2. So my critical point is 2, -2. And it does have to be in the region, right? If it's not in the region that we're looking at, it doesn't count. We don't bother with it. This one is, right? It's right there. So we have to test the corners, we have to test this point, and we also have to test any critical points on the edges. So yeah, so our edges, by the way, so our edges are, this edge is y equal to 0. This edge is x equal to 0. This edge is y equal to -3. And this edge is x equal to +3. So we're going to take each of those things, plug those into the original function, and then take the partial so that we can find the, we'll take the derivative so that we can find the critical values there. So let me write my function again. Let's see. So I've got, what do I got here? 2 plus 2x times 2y. Minus 2. Okay. So then on the edge y equal to 0, right? That's one of them. I'm going to have f of x comma 0 equal to, let's see, so I'm just plugging in 0 for y. So I get 2 plus 2x, 0 minus x squared, 0, 0. And then I take the partial with respect to the only variable that makes sense, x. I get 2 minus 2x. So that equal to 0, you get x equal to 1. So 1, 0 is a critical point on the edge y equals 0. So here's y equals 0, here's the point, 1, 0. So that's a critical point. Okay, we do the same thing for x equal to 0. So I set x equal to 0, I get f of 0 comma y, which is 2 plus 0 minus 2y, 0 minus y squared, 0. Taking the partial, I get -2 minus 2y, set that equal to 0. And I think I get y equal to -1. So that ends up being at the point 0, -1, which is also in our region. All right. Then we've got the other ones, y equal to 3. If y equals 3, I've got my function x comma 3 is going to be 2 plus 2x minus 2 times 3 is 6 minus x squared minus 3 squared minus x times 3 is going to be 3x. And at first I was doing this and I was like, oh, it's not going to make a difference. It's going to be the same as over here, but it does make a difference. Because before, when you plug in y equals 0, you didn't get this x times y terms. But now when you plug in y equals 3, you do get 3 times x, so you're going to have a different derivative. So the partial here, this problem's a long problem. It is, let's see, 2 minus 2x minus 3, set that equal to 0. You get 2, let's see, I don't know. Interesting. Actually, one sec. Yeah. Haha. Oh, good. I was hoping for this. I thought I'd made a mistake, or I thought I had made a mistake and I didn't get what I wanted. This is great. So let's see. Solving for x, I get 2 minus 3 equal to 2x. I get x equal to -1/2. So -1/2, 0 is a point, but -1/2, 0 is over here. And that's not in my domain, right? X is in between 0 and 3. So we don't include this point because it's not in the region that we are bounded by. So definitely look out for that because it happens sometimes. Finally, plugging in y equal to 3, plugging in x equal to 3. Let me make sure I did that last one right. I just feel like I might. No, that works right here. I'm good. Yeah. Plugging in x equal to 3, same kind of thing. I get f of 3 comma y is 2 plus 6 minus 2y minus 9 minus y squared minus 3y. Ew, that's gross. Got a real nice big old dark mark on my pen there. And then taking the partial here, fy is going to be negative 2 minus 2y minus 3. So that equal to 0. Negative 2 minus 3 is negative 5 equal to positive 2y. So y is going to equal negative 5 over 2. And that is a point in my region, right? If x is 3 and y is negative 5 halves, that's negative 2.5, which is right there. Okay, so here are all the points we have to test. The true critical point, the critical points we found on each boundary. I feel like I'm doing something. Oh, just one small issue, not a huge deal. When I found that x equals negative 1/2, that's correct. But the point should have been, wasn't negative 1/2 0, it was negative 1/2 3, because y was 3. Oh, I'm dumb. I'm sorry, I made a small mistake, you guys. So I plugged in y equals 3. Y equals 3 wasn't my line. It was y equals negative 3. So let's go back and check it. Sorry about that. So if I actually plugged in, so what I was really having a problem with was I thought it was just negative 1/2 negative 3, but I don't. So let's see. If I actually plugged in y equal to negative 3, I would get 2 plus 2x plus 6 minus x squared minus 9 plus 3x. And then my derivative will be, so it's going to be negative 3 and negative 3. My derivative will be derivative of 2x is 2. Derivative of negative x squared is negative 2x. But the derivative of 3x is positive 3. So I end up with 2 plus 3 is 5 equal to 2x. X equal to 5 halves. So I do actually get this point. So 5 halves, comma negative 3. It's always good to check your work. So I have this point here. 5 halves, comma negative 3. All right, so check this out. We have 9 points to check. We have the one critical point we found at the beginning. We have the 4 critical points we found that all ended up actually being in the boundary. And you don't have to check ones that aren't in the boundary. You shouldn't check ones that aren't in the boundary. And then we also have to check all 4 corners. Okay, I'm going to do a little bit of erasing. So the rest of this is really just arithmetic. We just have to check f of 0, 0, f of 3, 0, f of 0, negative 3, f of 3, negative 3. Those are the 4 corners. Then we have to do the other critical values we found. F of 1, 0, f of 0, negative 1, f of, these ones are going to be kind of a pain. F of 3, comma, negative 5 halves, and f of negative, sorry, 5 halves to negative 3. And finally, this one in the middle, f of 2, negative 2. And then we calculate each of those and then figure out which one's the biggest and which one's the smallest. So let's do it real quick. So f of 0, 0 is 2 plus a bunch of zeros. F of 3, 0 is, let's see, 2 plus 6, 0, minus 9, 0, 0. So 2 plus 6 minus 9 is negative 1. F of 0, negative 3 is going to be 2, 0, plus 6, 0, minus 9, also negative 1. 3 negative 3 is going to be gross. It's going to be, let's see, 2 plus 6 plus 6 minus 9 plus 9. Let's see, 14 minus 9 is 5. Again, this isn't the important part, right? I feel like we should just kind of like go past this, but we'll finish off real quick here. If of 1, 0 is going to be 2 plus 2 minus 1, which is 3. F of 0, negative 1 is going to be 2 plus 2 minus 1, which is 3. And then these ones are going to be gross. Fine. Let's do this one. F of 2, negative 2 is going to be 2 plus 4 plus 4 minus 4 minus 4 plus 4, which is 6. And finally, this one is going to be 2 plus 6. Negative 2 times negative 5 halves is plus 5 minus 3 squared to minus 9 minus negative 5 halves squared, which is minus 25 fourths minus xy, which is going to be plus 15 over 2. And that is something, let's see, let's see, 2, 8, 13 minus 9 is 4 minus 25 fourths is 6.25. 15 halves is 7.5. So that's 1 1/4 plus 4, that's 5 1/4. All right. I'm not going to do the last one because it's probably the same. So here's what I would say at this point. Assuming that this is the same as that, which is pretty safe, I would have a global maximum at these 2 points, because that's the biggest z value. I have a global, no, I'm wrong. Sorry. Here's the global maximum at 6. Sorry, at 2 negative 2 with the value of 6. So I have a global max at the point 2 negative 2. And I have global minima at 3 0 and 0 negative 3, because both of those are the smallest values being equal to negative 1. Kind of a long problem, but that's how you would do one like this. Okay, so here's the attendance again. So I know we only have like 5 minutes left. Let me look at one of these optimization types of problems in chapter 9.6. Unless there's something else that's really pressing. I don't imagine there is, but never. So, I know my phone's in my pocket's hot. My phone's in my pocket. Okay. Let's see here. Sure. To find the dimensions of the largest rectangular box, where'd you go? If the surface area is 64 square centimeters. All right. So this is very much like optimization before, where you usually have a function of 2 variables and you have a constraint where you write one variable in terms of the other so that you can have a function of 1 variable. So now we're going to have a function of 3 variables, or an equation of 3 variables, no, a function of 3 variables, and then we're going to have a constraint to get rid of one of them, and then we're going to use our 2 variable methods for finding maximum. So I want to find the largest box, meaning I want the most volume. If I have a box that looks like, this, this is x, this is y, this is z, then the volume is just the product. But again, we don't know how to find a max or a min for a function of 3 variables, but we do for 2 variables. So we use this constraint here. The surface area is 64 square centimeters. Well, the surface area is just the areas all added together. So it's, x times y plus y times z plus, x times z, y times z, x times y, and then double that because there's 2 of each edge. So it's really 2xy plus xz plus yz. And that's supposed to equal 64. So what we're going to do is we're going to use that equation to solve for one variable and plug it back into the other function. It's kind of gross. Let's see. So divide by 2, xy plus xz plus yz equals 32. And then I'm going to solve for z because that kind of feels natural, right? This is pretty symmetric in all the variables, so I'm going to solve for z. Let's see. So xz plus yz equals 32 minus xy. and I can factor out a z. So z times x plus y equals 32 minus xy. So z equals 32 minus xy over x plus y. So, what time is it? Okay. I'm not going to finish this problem today, but we can finish on Monday. The idea here is that then we can write the volume as a function of just x and y. It's going to be x times y times z. So then you've got a function of two variables, and then you can do the usual things. You can find the critical points by setting the partials equal to 0. And then once you find your critical points, then you can figure out whether they're maxes or mins by finding z, which is going to be vxx vyy minus vxy squared. It's going to be a little bit gross, I'm not going to lie. Taking the derivative of this with respect to x and y is going to be not nice, but that is the process. We can definitely finish this one off on Monday if you guys want, but remind me about it because I might not remember by the time we get to Monday. So, all right, that's all I've got for today. For those of you in Rademacher's class, remind your friends who weren't here today, like Eric and Cameron, who I don't see, that I did this today and they might want to look at it. And for those of you who aren't in this class, if any of you have questions from Carlson's class, first of all, I'm sorry, his test looks terrible, or his practice test looks terrible. But if you have questions about his practice test, shoot me an email or start a discussion. Also, when is he giving his test? Monday, okay. What time is his test at, or is it all day? Oh, it's due on Wednesday, okay. So we can definitely, I will look at his test when you guys actually get it, and I'll try to come up with some good questions that aren't actually the questions he's giving you guys, but will help you kind of get through it. So that's what we'll probably do some of Monday, and then we'll also look at what Rodriguez, I'll make sure to go watch Rodriguez's lecture so I can see what you guys have been doing there, and we'll try and cover all the things. All right, have a good weekend. Good luck for those of you taking a test today, and we'll talk to you all later. Bye. Make sure you do the attendance. Bye.
Thank you.
Welcome. You're all welcome.